Hi, I'm Jeff Rosenfeld. I'm editor of the Bulletin of the American Meteorological Society. We're here at the annual meeting of the American Meteorological Society, which means it's a great time to talk to experts. And we happen to have the expert here on the AMS because we've got a past president and pretty much everything else. Marshall Shepard from the University of Georgia. And Marshall's research area has included a lot about precipitation and how urban climate affects the environment around the city.
Sure.
And downstream, right?
Yeah.
So I'm just kind of wondering where's urban climate these days at the annual meeting?
Yeah, well, it's also, it's just not just urban climate, there's urban meteorology as well. The National Academy of Sciences just produced a report last year talking about the importance of urban meteorology and climate, because if you think about it, where do most people live? In cities. We're an urbanized society now. By the year 2025, 65 to 80% of the population of the world will live in cities. So when there's a flood or an extreme heat wave or a tornado barreling through downtown Atlanta, for example, it has an immediate impact against people's attention. So that's why the work that we are doing, I think, is very critical, because it's sort of apparent and obvious to people when there's a significant weather or climate extreme in an urban context. So.
And with everybody living in urban environment, does that make bigger effects on climate, say, than otherwise?
Well, that's interesting. Even here at the annual meeting here in Phoenix this week, we are presenting some of our new work on something we're calling urban climate archipelagos. Now, people are familiar with the urban heat island, which is the fact that the city of Phoenix or Boston or Atlanta will be warmer than the surrounding area. But what we are doing is advancing that concept from one island to the notion of an archipelago or a chain of islands. And so what we're finding is that their sort of integrated impact of cities can amplify heat, can cause changes to precipitation patterns, determine where the rain-snow line is in places like Boston, New York, Philadelphia, and DC because of the urban interactions. So the cities can not only affect weather, the weather in turn can downscale back and affect people in those cities.
And cities are often situated in complicated meteorological situations,
Sure.
right? Doesn't that make it difficult to research some of these things?
Yeah, absolutely. So, for example, one of the areas that we're focused on is what we call the megalopolis region from DC up to Boston, where the AMS is based. And so, in that urban corridor of big blobs of impervious surface which radiate heat, which also force the air to rise, and in some cases can produce or enhance thunderstorms. You also have mountain chains, you have complex terrain, you have bays and land surface interfaces that produce sea breeze fronts. So how these things interact to change weather and climate, that's certainly some of the things that we're going to be presenting here at this meeting. So,
how do you get down to the scales of interaction we're talking about? Because of the city, you're talking about the impact of people, right? They're walking around, stirring up the environment,
Sure.
their buildings. These are very small scale.
Yeah, well, it's a multi-scale problem. So you have this sort of urban canyon scale walking through the buildings in a city, but then you've got the large metropolitan suburban environment of a city itself, and they all have different impacts. And so the challenge is, understanding those different interactions of those scales. So, for example, one of the things I'm really interested in addition to urban processes of precipitation, I'm a member of this NASA precipitation science team, and one of the things I've been really interested in is whether we're seeing more occurrence of urban flooding. And I believe that we are, and we'll talk a little bit about that at this meeting. I think there are three reasons why. One, I think that because of the growth in urban impervious surface, more concrete and asphalt parking lots, things like that, when it does rain, the water doesn't seep into the soil, it actually just runs off into the lakes, they get full, and then you get flooding. Secondly, from a climate perspective, the scientific literature, many in AMS journals show that when it rains very heavily, the intensity of that rain is heavier than it was in the 50s and 60s and 70s. So that's secondly. And then thirdly, the stormwater management systems in cities like Phoenix, Boston, Atlanta are designed for what I call the 1960s and 1970s rainstorms. So engineers designed these drainage systems under the assumption of what we call stationarity, which is that the rainstorms of the 1950s will look like the storms of the 70s, which will look like the storms of 2014, but that's just not the case. It rains harder now.
How good is the climate baseline, the information database for that?
Yeah, and that's always a challenge. So we use these climate normals, these 30-year periods, but one of the things we're increasingly finding in the peer-reviewed literature is that these assumptions of stationarity are just flawed. I mean, engineers, there's some technical terms that we use called intensity, duration, frequency curves. Basically what these things are doing is saying, okay, how often does a 5-inch rainstorm in a 24-hour period come to Boston? And so statistics, they look back at sort of climate data to develop these 100-year, 200-year flood event type things. But the challenge is much of those sort of the engineering for the cities are based on data from the 30s through the 60s or so. So there's an effort or a knowledge to try to update those things, because we certainly know that those statistics are probably flawed now. And so that's why I believe we are seeing that. And it's not just a belief, but we see this in the peer-reviewed literature. And it gets to another aspect of the meeting here in Phoenix, which is communication and perception. Because most people, for example, when they hear 100-year flood, they think that's a flood that can only happen where they live every 100 years. And that's actually kind of a challenge, because that's not what that really means. It actually means there's a 1 in 100 chance that a flood could happen at any time in the year. So you could actually have 5 100-year floods this year. Just it's extremely unlikely that that will happen.
Yeah, but now this whole question of unlikely, I mean, we're talking about communicating probability.
Sure.
Right? So what kinds of progress do you see, or what hope is there to get that message across?
Well, it's a challenge because, you know, the American public, from a science and math literacy standpoint, most people are accountants or lawyers or doctors or plumbers. They're not scientists like I am. So people tend to have about an 8th grade science and math literacy understanding. So when we talk about things like statistics and probability, we as a community, we have to understand that people don't necessarily consume it the way we do. Even with the Atlanta snowstorm, we were in Atlanta last year for the AMS, and there was a big snowstorm of about 2 inches that shut the city down. And one of the things that social sciences studies have shown, and we've got quite a few social scientists here, they've shown that people were confused because in the National Weather Service system, it goes from a winter storm watch to a winter weather advisory to a winter storm warning. So when people saw it go from a winter storm watch to an advisory, they thought that was a downgrade, but it was actually an upgrade.
And there is a town hall, I think, at the meeting this week about advisories, warnings, and watches. And
that is correct. And we also, one of the other sort of hats that I wear is host of a show on the Weather Channel called Weather Geeks. And we are actually, for the first time, taping 4 shows here at the AMS. And one of those shows is Messaging the Weather, where we have Dr. Kim Koloko and Dr. Susan Jasko on talking about some of these very issues in one of the shows.
Now, speaking of, the latest in communication, obviously you're at the forefront of that. You do a lot of social media,
Sure.
And you're doing the TV show,
Sure.
which is great. What about the latest in having drones flying around the convention hall and capturing conversations and really
Are
communicating
people
what's
doing
going on?
that?
I don't know. I'm wondering, is that where we're going with this?
Well,
We're talking about drones all the time.
Yeah, no, drones. We certainly use drones in some of our research to support some of the NASA missions that I'm involved with, some of the ground truth and validation of hurricane research and whatnot. But no, I think that we are getting into an area. There's so much data available, crowdsourced data, tweets. I mean, even in some of our research at the University of Georgia, we're using social media data, mining that to try to understand, what we can learn from a weather, climate, or applications perspective. We're trying to do some work to look at whether we can discern whether they're going to be. We've done some work at University of Georgia on thunderstorm asthma. We found that in the city of Atlanta after thunderstorms, there's an uptick in asthma response and hospitalization rates, and it has to do with the pollens being moved around by the outflow boundaries in the thunderstorms, and the rain breaking the pollen into smaller aeroallergens, and even lightning, because lightning produces nitrogen oxides, which exacerbates asthma. So one of the things some peer-reviewed literature has shown is people start tweeting more if they're having bad asthma response, and so we want to mine that and link that up with Doppler radar data to see if we can develop some kind of early warning system based on social media. So using these immersive data techniques and sort of the big volume of data and sort of personalized data, what Kathy Sullivan talked about in the presidential forum today, environmental intelligence, I think we are going to see very customized weather. I think what's the temperature or how much is going to rain today, I think those, as alluded to, are probably things of the past in about 10 years. It'll be a much more customized experience.
It does seem like there are a lot of younger researchers here who are really into the data mining, the big data questions, and how to use that to integrate all this different information. And when I think of urban climate,
Yes.
I think that's probably the nexus of a lot of this.
Yeah, I was at a meeting, the European Meteorological Society meeting during my year as president of AMS, and I was very fascinated by some new work being presented there that shows that our cell phones, when we I have one in my pocket right now, and the batteries in most of the cell phones actually regulate their battery temperature using the ambient temperature of the air. And so this study was showing that we can use that feature of phones to get very high density measurements of temperature in cities. You've got thousands of people walking around right now, so we could have a very high density measurement system based on people's cell phones. And so that type of thing. And then you've got the MPing project that NOAA, National Severe Storms Lab, is doing, where people can actually on the fly tweet whether it's raining or freezing rain where they are, or if it's drizzling. And so all that information goes into the cloud, and it's rich. So I think we're in a situation now where we can collect these things. What do we do with it? How do we? So much data, because scientists oftentimes we have so much data we have to efficiently be able to mine it and utilize it to extract signal.
Well, so when you reach for your cell phone, I don't know whether you're doing social media or whether you're doing research.
Exactly. And in some cases, it's a little bit of both, actually, these days, because as I said, we've done, we had a study where our colleague Don Knox, and he may be presenting some of that, looking at Facebook and how it was used to collect debris from the Alabama tornadoes several years ago. And from that information, he was able to extract trajectories of debris being wafted by tornadoes, and it was really interesting because it actually taught us some things about the dynamics of tornadoes. So,
well, I hope to learn a lot more this week. Thank you so much for your time.
No problem, too.